Hello and welcome to Empowered Learning. This is the fourth video in the Laplace transform video series. And so what we've done up to this point is we've talked about the Laplace transform as far as its definition and some of its constraints. We've also derived a lot of Laplace transforms for basic functions that we called suitable. And of course, we've already defined what that is in the part one video. If you need to know about that, please check out the part one video. If you need to see some examples of how to take a suitable function and apply the definition of Laplace transform to find what that is, then see the part two video. We've also talked about some special properties like the linearity and transformation, or some people call it translation properties as well as just seeing some basic examples of how to take the Laplace transform of a random function, which is the sum or difference of a lot of different functions with some constant multiples to them. So that was in the part three video. So this particular video, which is part four, what we will do is naturally kind of take it a step up and start talking about the derivative as well as the integral of a Laplace transform and vice versa. So our goal here is to kind of put the final touches on the tools that we need so that we can actually start to take the Laplace transform of an ordinary differential equation, and then from that figure out what the Laplace transform of our solution, and usually we'll call it like f of t or y of t. We'll find out what the Laplace transform of that is, which would be, let's see, big Y of S. So it'll look something like this. So big Y of S if my solutions are going to be little y of t. So, and that's really the goal that we're going to set forth for this particular video. I will have some other videos that follow that gives us more practice on actually finding this. And well, of course, the last video in this series will actually use the concept of an inverse Laplace transform to go from this back to that. Okay. So the four main things that we want to do for this particular video will be the following. So first, we want to be able to say, if I take successive derivatives of a function and I find a Laplace transform for, let's say, the nth derivative, what is that formula going to look like? And of course, this is important to me because I want to be able to know how to do stuff like, well, if I have a function and I need to find the third derivative of it, then I need to know, all right, well, what is the Laplace transform of the third derivative of some function? Okay. So that would be important for me to know if I'm trying to solve an ordinary differential equation and I need to take the Laplace transform of it. Okay. We're also going to see if I took successive derivatives of the Laplace transform of some function that I don't necessarily know, but if I wanted to find what the nth derivative of that is, well, how does that translate back to saying basically Laplace transform of what? Okay. So what would this look like here in the t domain or time domain if I was taking successive derivatives here? So these first two address what we need to talk about whenever we talk about differentiation. Of course, 3 and 4 are the analog of 1 and 2 as far as integration. So of course, with number 3 kind of matches number 2. If I was to take the antiderivative, or evaluate the integral of the Laplace transform of a particular function, what would that look like over here on this side? Okay. And similarly, if I had the integral of some function and then I took the Laplace transform of it, what would it look like over here in the S domain? So those are the questions that we're going to answer in this particular video. Now, for the sake of dealing with ordinary differential equations, objectives number 1 and 2 are going to be our primary focus. I am going to state basic theorems that go along with objectives number 3 and 4, but we won't spend a whole lot of time on those. Of course, because most of what we're going to see is dealing with objectives 1 and 2 here. All right, so let's begin with looking at our first example where we're just trying to find a Laplace transform of the first derivative of some function. And again, the goal here is for us to do the Laplace transform for successive derivatives so that we can see a pattern and then figure out what that pattern is, so that no matter what order of derivative we need to find a Laplace transform of a function for, we'll have a ready-made formula to be able to do that. So in this first example, we just take the basic definition of what a Laplace transform is, and in place of where the function would usually be, we have the derivative of that function. Naturally, we see here that we would use integration by parts to be able to evaluate this improper integral. And naturally, since we have the derivative of some function, if we let that be the dv dt, then of course the antiderivative of that would just be f of t, which of course is convenient. And we'll let u be e raised to the minus st. Take the derivative of that is just the constant negative s times e raised to the minus st. Pretty simple. So we do that, and then we substitute what we need to into the formula for integration by parts. And we simply just know the integral of u dv is equal to uv minus integral of v du. So we're just applying that. But since we have limits of integration that go from 0 to infinity, we have to add in all the proper notation whenever we have improper integrals that we deal with, because this is one of them. And hence why we have the limit as b approaches infinity here, because we'll have to apply the net change theorem like we're integrating a definite integral, and then from there apply the limit. So we've seen this sort of thing in the other videos before, just kind of mentioning it again so that I can kind of go faster as we go through all these derivations here. So for the first one, we just get everything set up. For the limit here, I know that my u is going to be e raised to the minus st. My v is going to be f of t. And so I'm taking this term and I'm going to go ahead and work out and see what that is. And then afterwards, I'm going to deal with this term and figure out what it is and then put it together. So that's what you're looking at here. So if we look here, we know that in general, f of t has to grow slower than e raised to the st. But since this came from a definite integral here, we're going to have to actually do the whole net change theorem first. So we have to plug in b everywhere where we see t, minus plug in 0 everywhere where we see t, and then take the limit of what's left. So here we see that the limit operator, its variable is b. So f of b and e raised to the sb looks like a function to it. So we'll actually have to evaluate this limit, and that's what you see here. Of course, f of 0 is just some constant, and so the limit of a constant is just that constant. Okay. Now we know that for some function f and e raised to the sb, we know that in order for f to be Laplace transformable, this function here would have to grow slower than this one. Okay. And because of that, we know that the limit of any function that grows slower than e raised to the sb is going to have to be 0. Okay. And so all this business that I have down here is just a real fancy way of saying that. Okay. And for those people that like to talk about things in terms of exponential order, I've sort of addressed that here. But just in general, we really don't have to be this verbose. All we need to know is that, hey, whatever this function is has to grow slower than that one. So limit as b approaches infinity has to be 0. So if we move forward here, we can take care of the next term because of the fact that here, the only thing that we have left is minus f of 0. So this result here is just going to be minus f of 0. Okay, whenever we evaluate this first term here, all that's just going to be minus f of 0. Okay, so now we're going to focus on evaluating this integral. And so we go ahead and put all that information in, and we notice that we have this constant minus s that can be factored out. And if I ignore that part, notice that what I have left is exactly what the Laplace transform of some function f of t would be by definition. Okay, so that's why here we just say that, hey, by definition, we know the rest of this is just a Laplace transform of it, and that's just that multiplied by some constant minus s. So when we put those two things together, the first term was minus f sub 0 minus, and then a negative s times Laplace transform of little f of t. Of course, these two things combine to be addition, and we have this formula here where the first derivative will be s times the Laplace transform of little f of t minus the constant f of 0. And so we'll start looking at the Laplace transform for the second derivative, and we'll see that it'll kind of follow suit, the same kind of, I guess, process of being able to derive it. But one special note we want to look at is that if my function f of t is going to grow slower than e to the minus t, or if I wanted to look at it in terms of f of t divided by e raised to the st, f of t is going to either increase or decrease, however you want to put it, slower than this exponential here. So if it does that, then of course any order derivative, so the first derivative, second derivative, third derivative, fourth derivative, we know that all of its derivatives are going to also grow slower than this function as well. And we know that because, again, if I go back to all the mumbo jumbo that I had here, whatever f of t is, it can't be more than this function here. So whatever the derivatives of this acts like, this has to follow suit, meaning that however fast this grows, this has to grow at least as well, it has to grow that fast or slower. Okay. And so we're going to keep that in mind, and that's going to help us to be able to actually get through some of this derivation for the second, third, and fourth derivative relatively easy here. So if we look at taking a Laplace transform of the second derivative, of course, we just follow the definition again, identify what our u and dv would be, and then just substitute everything in. We know that what we're looking for here is just going to be integral of u dv evaluated from 0 to infinity. Of course, the first term here is always uv, but since we have a quote-unquote definite integral here, we're going to have to evaluate it from 0 to b, where b is infinity. And then, of course, we have to evaluate integral of v du. So we kind of know what to expect here. So we just plug in everything for this first term. So we're going to figure this out first. So we plug in everything for the first term. We see that we get this. I've rewritten what's over here to make it look this way so that whenever we evaluate the limits, a little bit easier to deal with. So if we plug in b everywhere where we see t, minus, do the same thing with 0, then of course this is still just 1. F prime of 0 is a constant, and the first derivative of f at some, and I'm going to call it variable b because b goes to infinity here. Whatever this is going to go slower than whatever this particular function is here, and that was the reason why I mentioned this here. So we know that this particular limit for this particular term will just go to 0. The limit of any constant is just that constant. So again, we get just minus some constant. And of course, the constant this time is just the first derivative of our, it is just the first derivative of our function evaluated at 0. So do the same thing for the second term, plug in everything, factor out that s again, and we see that what we have here left is actually the definition of the Laplace transform of that function. And what should be here, I think that's missing here, it should be a f prime right here, because I have f prime there, so f prime should be there. And of course, this is just a Laplace transform of the first derivative. And from here, we know that, of course, that is this, so we'll just multiply all of this times minus s, and this is the result that we get. So once we put it all together, we see that the first term was just minus f prime of 0, minus, and then of course we have all of this here from the second term, and we see that this ends up being s squared, Laplace transform of f minus s times constant f of 0 minus f prime of 0. So we continue on with the third and fourth derivatives. I won't go through all the details again, but pretty much follow suit what we do. Here, let your u still be this, let your dv be the third derivative of f times dt. We do all the work again, and we'll see we're going to follow a similar pattern. And so as we work it out, we see that, of course, when we take the limit of the second derivative, basically doing this term here, whenever we do all that, we see that we get minus second derivative evaluated at 0, which is what we kind of expected. And of course, when we do the second term, and so this term here, whenever we do that, we get something that looks like this times a minus s. And again, kind of what we were expecting. And so we see that the third derivative, if we take the Laplace transform of that, in general, we have this situation here, and this is a mistake. This should be s cubed times Laplace transform of f of s. So glad I caught that. And so from here, we've seen enough to kind of see a pattern. So if we list the first, second, and third derivatives together, you kind of see that we're always starting off with s to the, whatever power here kind of matches the order. So this would be s to the 1, s to the 2, s to the 3 times the Laplace transform of the function. And of course, here we see that the last term is always minus whatever this function is minus an order. So of course, this is first order. So order 1 minus 1 is 0, which is just the constant function itself. Order 2 minus 1 will be the first order. So minus the first derivative evaluated at 0. Order 3 minus 1 is of order 2. So we have minus the second derivative evaluated at 0. So we always know the last term is that. The in-between terms, of course, as we see here, this would be s raised to the 1, order of 0 here. And for the third order, we have s raised to the 2, order of 0, and then s raised to the 1, order of 1. And of course, we see how this goes from 0 order, first order, second order, whereas here this goes from third order to match this, second order, first order, and then of course here we could put in an s raised to the 0, which would be 1 essentially. So we see how the s's go down in the exponent, the f's go up in order as far as the derivatives are concerned. And if we kind of put that together in a nice compact formula, this is what it's going to look like. And so this is one of the main things that we need to know in order to solve ordinary differential equations, because again, we know that differential equations are equations where a lot of the terms involve derivatives of some function that we don't know. And of course, the goal is to figure out what that function is that's going to satisfy that differential equation. So now that we have this formula here, we could do things like, well, let's find the Laplace transform of the sixth derivative of some function. And we could literally just use this formula and just write out what it's going to be, okay? Now, one of the things that you notice here is that if we're talking about, let's say, the sixth derivative of some function here, then we're probably going to need to know a lot of initial conditions, okay? And particularly, we need to know the initial conditions from everything of f of 0 all the way to the fifth derivative of f evaluated at 0. Or we could choose some other value, but we'll mainly start off at t equals 0 for most of these. And so if we said that all the derivatives from basically the first derivative to the fifth derivative, as well as the original function itself, if all those equaled 0 when t is equal to 0, then of course all these terms that you see here would just collapse to 0, and we would end up just having s raised to the 6 times the Laplace transform of whatever our function f is. Now, if we had different values here, then of course different numbers would go here. And at that point, of course, we would have to deal with that when we get to it, whenever we start to deal with trying to solve ordinary differential equations. But as of right now, we're just trying to make sure that we understand how to use this formula here. All right, so now we've seen how do we take successive derivatives of a function so where we get to the nth derivative, take the Laplace transform of that, and we see what formula that comes out to be. So we understand what that looks like now. Next thing that we want to figure out is the Laplace transform of what kind of function is going to be equal to the nth derivative of the Laplace transform of some function, okay? So we're trying to go the other way. And so we're going to figure out, well, the first derivative, second derivative, third derivative, fourth derivative of the Laplace transform of a function. What does that look like? And how could we back into figuring out what that corresponding function should look like over here in the t domain? All right, so now let's do exactly what we said. Let's figure out what the first derivative, second derivative, third derivative, and fourth derivative of the Laplace transform of a function is. And from that, try to establish some kind of pattern so that we can figure out what corresponding function would translate into saying, hey, if you take the Laplace transform of this particular function, then that will be the same as taking the derivative of the Laplace transform of this order, okay? So the first thing that we see here is that, of course, if we want to rewrite big F prime of S, then that's the same as just df over ds if we want to put it in Leibniz notation. And if we look here, we know that by definition, Laplace transform is an improper integral, okay? Now, what we know about the fundamental theorem of calculus here is that the integration and derivative operators, we can switch the place of them, okay? Because they are literally supposed to undo each other. So here we can slide this derivative operator on the inside of the integral here. And so now once we look here, okay, one of the things that we notice is that since this derivative is going to be a derivative with respect to s, this function here only has function of t. And so assuming that f doesn't have any constants in it that look just like S, okay, and we can assume that, then here the only thing that we're going to be able to take the derivative of here is this. And of course, to this derivative operator, we see that S looks like the variable and T looks like the constant. So from that, what we can essentially do is pull out the f of t out of the derivative part and just evaluate what's going to be the derivative of e raised to the minus st. Take the derivative of that with respect to s. Okay. Now, I know that I am doing this, and there are some things that I guess to put it another way, we're kind of blindly doing this, but there are some special conditions that f would have to have in order for us to be able to do this and assume that it can happen for any situation. Okay. And it really can't happen for any situation. It's saying that, hey, what it is that we're trying to do here, we can only do it if f meets some conditions. Now, to make a long story short, because me going into all the derivation for showing, hey, what conditions does f have to have in order for me to be able to do what I'm about to do, is really out of the scope of what we're trying to do here. I'm just going to say that the conditions that satisfy f for being Laplace transformable are pretty much the same conditions that we need for us to be able to do what we're about to do down here. Okay. So I'm going to simplify it that way, and we'll just take my word for it and move on. So for here, in us trying to evaluate the derivative of this, we see that this looks like a constant to it. And of course, to s, t looks like a constant. So I'm essentially just going to switch this from taking what I call the whole derivative to the partial. Okay. And so in doing that, we just take the derivative of what e raised to the minus st is, ignoring the f of t here. And we see that we just get minus t e raised to the negative st, because again, t looked like the constant. And so here, if we were to rewrite this, notice that this is in the place of the function that we would do the Laplace transform on. And I'll just call it g of t here for a second, just to make sure that it's different. So we have e raised to the minus st times some function, integral of that from 0 to infinity. By definition, that is a Laplace transform of whatever's inside of here, my g of t. And so in this case, it just so happens that my g of t is just minus t times whatever that function f was. Okay. So we see here that if we know what the function f is, and we multiply it times a negative t, then that's the same as saying we know what the first derivative of the Laplace transform of that function looks like. Okay. If we were to take the Laplace transform of this. So we know what the first derivative of the Laplace transform looks like. Let's see what the second derivative looks like. So if we follow that similar pattern here, rewriting everything, and then of course switching the place of the integration symbol and derivative, and then from here, knowing that f is just going to look like a constant to this derivative operator, we go ahead and slide that in, factor out the f of t, and then just take the second derivative of e raised to the minus st. We take the second derivative of it, it'll just be minus t times minus t e raised to the minus st, which is what you see here. Of course, that simplifies to t squared times f of t. And we see here again, this particular function is kind of like our g of t. So we're taking a Laplace transform of g of t, because this by definition says that, and my g of t just looks like t squared f of t. Okay. So notice here for the first derivative, we know that the Laplace transform of negative t times f of t is going to be the function that we would have to be able to get the first derivative. And for the second derivative, see, we have t squared times f of t. So we're starting to kind of see a pattern emerge where if our order of derivative is odd, we're going to have a negative t raised to the whatever the order is. And of course, if it's even, it's going to be positive t raised to the whatever the order is times f of t. So we're going to do this again so that we can confirm that pattern before we make a decision on what the nth derivative of a Laplace transform is going to be. So if we do it again for the third derivative and go through all the steps here, I'm not going to bore you with the details, we see that we indeed end up with negative t raised to the number matches the order times f of t. That's going to be the function that we would have to take the Laplace transform of to figure out what the derivative, third derivative of the Laplace transform of whatever this is to do that. And then, of course, if we do the fourth derivative, we kind of see same thing happen here. Since the order is even for the derivative, we know that we have positive t raised to the whatever that order is times f of t being inside the Laplace transform here. So if we look at everything together, it's pretty much what we said. And we said that if we take the Laplace transform of, and let's say negative 1 raised to the n times t raised to the n times f of t, whatever that is, then taking the Laplace transform of this is the same as saying, let's just take the derivative of the nth derivative of the Laplace transform of this particular function here. And so that helps because now we don't have to do this whole thing of trying to, do the integration every time. We can just say, hey, if I want the second derivative of the Laplace transform, I just find out what the Laplace transform of f of t is, and then I can rearrange this equation here to figure out exactly what that's going to be, okay? And so to summarize what we've done so far, we know what the Laplace transform of the first derivative is, Laplace transform of the second derivative, Laplace transform of the nth derivative of some function in the time domain. We also see here that the first derivative of the Laplace transform of some function is going to be the same as the Laplace transform of minus t f of t. The second derivative, the function inside here is t squared f of t. And for the nth derivative, we see there's going to be t raised to the n f of t inside of here. But of course, we have this negative 1 raised to the n. If n is odd, then of course it's negative. If n is even, it's going to be positive. And now if we rearrange this equation, let's see which one. Yeah, we rearrange this equation here, we get this equation double star. Basically, we're just dividing both sides by this negative 1 raised to the n here. And so we see that if I wanted to figure out, let's see, t cubed times some function f of t, and I wanted to figure out the Laplace transform of it, I could just focus on figuring out what is the Laplace transform of f, do that, and then take the nth derivative. Let's say in this case, it'll be the third derivative of whatever the Laplace transform of this is. And let's say since n is 3, then I know that this quantity will end up being negative. Okay. And so that is how we figure out what the nth derivative of the Laplace transform of some function would end up being, and what function would produce the nth derivative of a Laplace transform. Okay. So we've covered this second objective here. So moving right along here, so just like we have used the identities above that we talked about to address derivatives in the Laplace transforms, we also have similar identities that we want to address. Number one, how to find the Laplace transform of a function defined as an integral. And two, how to find the integral of the Laplace transform of some function f of t. Okay, and so like I said at the beginning of this video, we're not going to focus so much on trying to derive those per se. We're going to state it so you can see what it looks like, and then we're going to move on from there. Because again, we mostly focus on the first two objectives that we talked about, but sometimes it is good to know these integral ones because it may help you get out of a jam sometimes. Okay, so we'll state this first theorem. We want to find the Laplace transform of the integral of some function. So if we let f be a continuous or piecewise continuous function on this interval from 0 to infinity, and of course that includes 0 to infinity open, just in case your function is not defined at t equals 0. And we know that our function, in order for it to be suitable, aka to be Laplace transformable, it's going to have to meet this condition here. And this simply says that whatever function f of t is, it is going to grow slower than the function e raised to the st. Or if you look at it in terms of e raised to the minus st, the f of t is going to decrease slower than this one decreases. Okay, or the rate at which this one increases is still not going to be as fast as how much this one decreases. So if we have that, along the fact that it's going to be a piecewise continuous function, or just a straight up continuous function, the fact that this is a function automatically meets that third condition of the relation being well defined. So once we have all that squared away, then we can say, since f is going to be continuous or piecewise continuous, and it's going to meet these other two conditions of being well defined and this limit satisfied here, then that means that its corresponding integral from 0 to t is also going to be another function that's going to be continuous and piecewise along this particular interval as well. Unless, of course, we have a situation where the function, because of doing the integral, is not defined at 0, and then we could possibly do this. Okay, so if all that's in place, then we can simply say that the Laplace transform of the integral of some function f, and I'm just simplifying it here to just g of t here, would be the same as taking the Laplace transform of your function and dividing it by s. Okay, or put another way, the Laplace transform of g of s, which is just a succinct way to say the integral of f, is going to be just the integral of, the Laplace transform of f divided by s. Okay. Now, what this is essentially telling us is that if I was to take the integral of some function and then do the Laplace transform of it, it's the equivalent of me just taking the Laplace transform of the integrand here and then just dividing it by s. Okay. So what I'm essentially saying here is that if I want to figure out what's going to be the the definite integral of some function here that I have a Laplace transform of it, I can just simply divide it by s, and that's what it's going to give me over here in this domain. Okay. Anytime that I take the Laplace transform of a function and divide it by s, then what I'm essentially doing over here in the time domain is I'm taking the integral of it, or evaluating the definite integral from 0 to whatever t is. So whenever I do this action over here, dividing this by s, it's the same as doing the definite integral over here to the function in the t domain, or in this case, I have it the tau domain. Okay, and vice versa. If I take the integral of this particular function over here in the tau domain, that's the same as taking the Laplace transform of my integrand and dividing it by s in the s domain. Okay. All right, so now we'll look at it the other way. Okay. Let f be some continuous or piecewise continuous function on this particular interval here. or possibly the interval 0 to infinity, where the function is defined at t equals 0. And of course, same conditions again. F has to grow slower than e raised to the st, or it has to grow slower than e to the minus st if we write it this way. Then we also want to note that if we take some function g of t and we define it as another function f divided by t, that's defined for this interval here. And of course, it would have to be this because, of course, t is in the denominator. So 0, if we plug in 0 for t, g of t won't be defined for that. We would also have to meet the condition here that the behavior of the function g of t, which is the same as f of t divided by t, as t approaches 0 from the right. So we're talking about some function here. Let's say, I'll just say it's 1, but it could be any value. We're saying here as t approaches 0 from the right, the behavior of this function is going to have to go towards some y value, okay? Whether it's defined there or not. And so here, probably need to do it more so like this to get it looking the way that it's supposed to. So this really should be like an open circle like that. So what we know here, function has to be continuous or piecewise continuous on this interval. We know that f has to grow slower than this function. We also know that f of t divided by t, as t approaches 0 from the right, the limit's going to have to exist. So if we meet all those conditions, then we also know that g of t, which is going to be basically f of t divided by t, is also going to be continuous on this same interval of t values. And this says, and it's of exponential order s of 0, just basically saying g of t is going to grow slower than e to the st or e to the minus st as well. So if it meets all that, then we see here that if I wanted to take the Laplace transform of g of t, which is just f of t divided by t, then we see that that's the equivalent of saying, hey, let me just take the Laplace transform of this particular function and evaluate it from s to infinity, okay? So we see that we'll get some function. If I could rewrite it as f of t, which that would be something that I know the Laplace transform of, and divide that by t. If I could rewrite this to make it look like that, where I know the Laplace transform of this, then to figure out what this is, I simply just take the Laplace transform of f, take the integral of that from s to infinity, and that would give me what the Laplace transform of this function g of t would be. All right, so now we see that we've taken care of all 4 of these objectives here. And again, for the third and fourth one, we just wanted to state it. So I'm not going to do any significant examples with those. But I do want to kind of go back to these first 2 objectives here and look at an example that would apply to at least one of them. In particular, I'm going to look at objective number 2 here. And so if we go back and we look at example number 5 here, we want to see what is going to be the third derivative of the Laplace transform of f of t if f of t is going to be e raised to the 3t here. Okay? Now, before we begin, we want to recall that whenever we take the Laplace transform of t raised to the n times f of t, that's going to be the same as -1 raised to the n times the nth derivative of the Laplace transform of this function f here. Okay, so we want to take that into account. So if we do that, we see that our f of t is just going to be e raised to the 3t. And here I'm purposely not putting in the 3 yet. I'm waiting until later to do that. So here we see that in doing this, we know that the Laplace transform of t raised to the n of this is just going to be this situation here. Now, where did this come from? Okay, let's talk about where this came from. If we go back to what we discussed earlier about our transformation properties here, and I'm going to go to the tables here to kind of see where that is. So I'll scroll down here and you should see it. So if you notice, we're dealing with a situation that's kind of like this situation here. We have e raised to some constant times t, some function here, and we see that in order for us to take the Laplace transform of something like this, it would just be the same as a Laplace transform of f of t, but we're going to have a horizontal shift in the S domain, or in the Laplace transform domain here, okay? So if we go back here, what we're actually seeing is we're going to take the Laplace transform of t raised to the n, and I'll go back to the tables again for that. Laplace transform of, I'll do it on the first page here. Laplace transform of t raised to the n is just n factorial over s raised to the n plus 1, where s is greater than 0, n is 1, 2, 3, whatever. In this case, it's going to be 3. So we see where this particular phrase or expression comes from. But notice we have here the s minus alpha here, okay? And so this looks like an a, but it's supposed to be, well, actually, yes, because of that a right there. In the tables, we have it as alpha, but of course, here it's going to look like a. And so all we're saying here is that whenever we have the situation of having our function being multiplied by e raised to the 3t, then of course that's going to be times a horizontal shift in the S domain. And of course, a here is 3. So we're going to substitute that in, and you see that right here. Now, I want to go ahead and move forward here in this table for a second, because do you see that we've actually got this in our table directly, okay? But now you see how we actually got it. We're actually using 2 different Laplace transform facts, and we're putting it together to be able to say that, hey, Laplace transform of a function that looks like this will actually end up being this particular expression here. So now if you were looking at this table or saw something like this, you know how we actually came about getting it. So now that we have that, then of course the Laplace transform of t raised to the n of 3t is just going to be this situation here, where we're just going to take the nth derivative. Of course, in this case, the derivative order is going to be 3. And again, since this number, the 3, and this order matches, I'm trying to do it separate so that we don't get it confused and think that it's always supposed to be like that, okay? So once we're here, then of course, we know that this expression here, the n factorial divided by s minus 3 raised to the n plus 1 is going to be equal to this. And we know because of that, the nth derivative is just going to be this. And again, the only thing that's really different is it going to be negative or positive? Well, the 3, which corresponds to the order of our derivative, takes care of that. And so once we plug in that 3 here, we plug it in here, and we plug it in here, then we'll see exactly what it is that we're supposed to get. And of course, we'll plug it in there. So we have our 3 here, 3 here, 3 there. then of course our third derivative of the Laplace transform of our function e raised to the 3t is going to be essentially this. So third derivative of the Laplace transform of this is just basically going to look like this. And we used our Laplace transform identities to be able to get to them. So now we're at a point to where we've kind of taken care of how do we deal with derivatives and integrals with Laplace transforms. So I'm going to end this video just showing you a nicer version of Laplace transform tables. And for most of you, if you are taking a differential equations course or a course where you're actually having to do these Laplace transforms, more than likely you're going to be given a table or allowed to provide yourself with a table, because normally we don't try to keep all these things in our mind. But again, just know that your tables could be as extensive as you want them to be. I'm just showing you a basic table here. So of course we have all the basic ones. 1t, t raised to the n, 1 over square root of t, t raised to the alpha, where alpha is just any real number that's greater than -1. You have your exponentials, cosine and sine, your step function and your step function with a time shift. And so we also see the definition of the Laplace transform for function f of t. We see here again the shift in the horizontal shift in the s domain if we multiply our function in the t domain by e raised to the alpha t. First derivative of f, Laplace transform of it looks like this. Second derivative, and then the nth derivative. We have t raised to the ft is negative first derivative of Laplace transform of f. T raised to the n f of t, which is what we just got through dealing with, is -1 raised to the n times the nth derivative of Laplace transform of it. And of course we have this one here, which mimics the same thing this does here, just letting us know that we can kind of do the same thing using imaginary exponent here, or imaginary numbers in general. So this will conclude the fourth video. And so now that we've kind of done everything that we need to do, in the next video I'm going to record, we're actually going to start taking the Laplace transform of actual ordinary differential equations at this point. Usually they'll have some initial conditions with it, and we'll use these tables that I've shown you here to be able to do that. And so I'm going to do several examples on that before we get into the Laplace inverse Laplace transform, rather, where we actually take our result from what we're going to be seeing in the next video and figuring out, well, what's going to be my actual solution to the ordinary differential equation. So I'll see you in the next video.